Welcome to Lab 5, Magnetic Braking with Faraday. In this lab, we are observing and collecting data from a magnet falling through a tube of aluminum foil. We will also create a computational model and compare our results. We are assuming in this lab that our bar magnet acts as a dipole. We're ignoring Earth's magnetic field, and we're assuming no air resistance. Important formulas and concepts include Ohm's law, Faraday's law, magnetic flux, Biot-Savart's law, Newton's second and third laws, and magnetic forces for a loop. In this experiment, we dropped a bar magnet north pole first to a stationary tube of aluminum foil. We determined how long it took to fall by analyzing video footage. Our system was the bar magnet and our surroundings were the aluminum foil and surrounding world. For our observations and results, we had a length of For our observations and results, the length of our tube was 0.33 meters, our foil width was 0.011 meters, the inner tube radius was 0.016 meters, and our outer radius was 0.027. We had a mass of 0.026 kilograms, a magnetic dipole moment from Lab 3 of 2.21, and our average time to fall through the tube was 2.7 seconds. Why can't we use a ferrous tube? Well, a ferrous tube would create its own magnetic field and interfere with our falling magnet, skewing our results. What happens to the magnet? How does this compare to falling in free space? In free space, the magnet would fall faster than within our tube, as the tube creates an upward magnetic force. The computational model simulated the same thing as our physical experiment. First, we create our tube using the same length and width as our original one. We then used our code from previous labs to calculate the dipole moment. We then created a loop, calculating the magnetic force as the magnet fell, and calculated the gravitational force on the magnet. We also calculated the change in flux to simulate our results. Finally, we changed our magnetic force into a vector, calculated the net magnetic force, applied it to our bar, and plotted it on a curve and on a graph. So what were our results? Well, as explained earlier, during the physical experiment, our average time to fall through the tube was 2.7 seconds. Our computational model calculated a time of 2.67 seconds. Some sources of error include errors when measuring the time taken during the experiment, incorrectly analyzing the video, and potentially an inaccurate dipole moment from our Lab 3 results. Some final questions. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. What color corresponds to clockwise current and which counterclockwise? How do you know? Blue is clockwise and red is counterclockwise, because you know induced current opposes changes in magnetic flux. What happens to the dynamics of the system when you flip the magnet around? The direction of the current would flip, but the magnet would still fall slower than when free falling in the surroundings. The idea is still the same. A current will oppose the falling magnet to create a magnetic force to push it upwards. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? They're very close, within 0.03 seconds, and we can make the computational system more accurate by simulating more rings in our tube. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? At the beginning and end, the gravitational and magnetic forces are unequal because we have acceleration. In the middle, we have a constant velocity telling us the forces are equal. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current would be larger, creating a stronger magnetic force and slowing down the magnet at a much higher rate. What if holes or slots were cut into the tubes? How would this affect the ring currents in your model? The holes would disrupt the induced current, resulting in a weaker magnetic force opposing the magnet, causing it to fall faster. In conclusion, we learned that the ferrous tube opposes the magnetic flux created by the falling bar magnet by creating a magnetic current. This slows the magnet down. We also created a computational model and got similar results. Thanks for watching.